Okay, welcome back. So this is the last lecture of this session, the first part of the unit, which is diode, MOSFETs, and BJTs. Okay, the next section is on differential amplifiers, and Dr. David Payne will be taking lectures for that. So sorry for the lack of audio in the last lecture recording. So I have put some videos to compensate for that in the iLearn. So they are freshly made videos, so you can watch them and let me know if you have any questions or some parts are missing. I hope it captures everything this time. Looks like it will. Let's look at the online quiz first. So more people got higher marks this time, which is good, but I would like to see everyone in that last two columns above 90, because these quizzes are really simple, and if you watch the video you should be able to score 100. So that also gives you an opportunity to see what you haven't understood or what questions you should ask me in the class or during the consultation hours. So one of the questions whom people made mistakes was this: at high VDS values, the channel tapers towards the drain due to what? Just go through that again. So we have our MOSFET with source and drain. If it is an N-channel MOSFET, both source and drain are N-type, which is embedded in a P-type substrate. So when a channel forms, it forms here, it's an N-channel. So when you apply but you see there are two PN junctions here at the source side and also at the drain side. This is a distributed PN junction along here and a PN junction along here. So this PN junction is not different from a PN junction of a diode, which is also a PN junction like that. So what are the properties of a PN junction? There is a depletion region between the P and N-type regions, right? At the junction, there is a depletion region. And electrons and holes cannot pass through that depletion region unless you apply a positive bias or forward bias. If it is a diode like this, you need to apply a positive to the P and negative to the N. So if you apply a reverse bias, which is a negative to the P and positive to the N side, it will enhance the depletion region. So it will deplete more and more carriers away from the depletion region or strengthen the depletion region. So we have a depletion region here and we have a depletion region here. So what happens when we apply a high VDS? VDS is positive at the drain and negative at the source. So that is like reverse biasing this diode like this, right? So it enhances the depletion region, and depletion region kind of depletes the electrons in this channel. So the channel width gets narrower towards the drain side. So the answer is due to reverse bias at the drain substrate PN junction. Okay, and the next one, what happens to the threshold voltage when the temperature goes up? Yeah, it's in the slides and the video. The threshold voltage goes down as the temperature goes up. So the only option here is C. It doesn't go negative. It doesn't increase. It can't decrease to negative, because as you see, to form an N channel, you need to repel the holes and attract ends. So no negative voltage can do that, right? So the threshold voltage doesn't, for an N channel MOSFET, it's always positive. VT is always positive. And in a P channel MOSFET, the VT is always negative. So you need a negative voltage to attract the holes and repel the electrons in a P channel MOSFET. Okay, so we will continue from what you have learned in the videos on the online material. So first, let's look at the small signal behavior of a MOSFET. So what you see here is a common source amplifier, right? Why is it called a common source amplifier? So source is grounded, but is that enough to call it a common source amplifier? Where does that common come from? The word common. Yeah, if you look at the small signal model, the input and output has a common terminal, and that is the source here. Okay, this terminal. So when you look at the input in a small signal model, this VGS, which is a DC power supply, is considered as a short. So one side of the VGS is grounded, and the output is taken across VDS, which is one side is grounded. So this is the common node. So that is why this is called a common source amplifier. It's a very commonly used amplifier too. So the amplification in a MOSFET is provided by the property where it acts like a voltage controlled current source. So you apply a voltage VGS, a small voltage, a small signal voltage as well. So it is not a DC but a AC voltage. If you change that voltage slightly, you can change the output voltage in a larger magnitude. So that's how it acts like an amplifier. So the input we give is VGS plus the small VGS. This is the DC part, and that's the AC part. So why do we need the DC part? You need to bias it first, right? So just giving AC is not going to make the amplifier work. So let's take a system as an example. For example, the audio system in this room. It takes power. It takes a DC power, even though we plug it in the power socket, which is AC. Internally, it is converted to DC, and that DC is powering the audio systems. So that is the DC bias. So if I don't speak, that amplifier is still on, that current is still flowing, it is dissipating some power or producing heat, dissipating some power. So the moment I speak, that is creating this small signal. Okay, that signal is picked up by the microphone, which is really tiny in amplitude compared to the DC applied to this system. And when I speak, all the amplifier is seeing is amplify my voice, not the DC. So this AC signal is corresponding to the small signal or the voice signal, and the DC here is the supporting DC bias or setting the cue point. Okay, I hope that is clear. Yeah. Especially if you're not from the electronics background, may be difficult to grasp, but I'm happy to help. Okay. So luckily for us, for MOSFETs, it's only one current that we need to find, the drain current, not like BJT where we have IC, IB, and IE, right? Although it was easy as well. So in saturation mode, so the amplifiers use, so use amplifiers, sorry, you use the MOSFETs in the saturation mode as amplifiers, right? Unlike BJT. In BJT, for BJTs you use the forward active mode for amplification, and for MOSFETs you use the saturation mode for amplification. So in the saturation mode you found that the drain current is equal to half Kn VGS minus VT the whole square. Okay? So sometimes people call MOSFET the square law device because the output current, ID, is proportional to the input voltage square. So in that sense, what is a BJT? So if you call a MOSFET a square law device, what do you call a BJT? No, you are not allowed to answer because I gave you the answer yesterday. So what do you call a BJT? BJT is an exponential device, right? Why is that? BJT, you know, IC is equal to I naught e power VBE divided by VT. Yeah. So it is exponential. So it depends on the input voltage VBE, or the exponential of that input voltage comes at the output, come out as the output current at IC. So let's look, just looking at the DC bias. So we have a DC voltage between the gate and the source, and another DC voltage between the drain and the source, VDS, which we call VDD. So ID is the same equation holds, but this is the DC current. So that is a constant ID that is flowing, the constant DC current that flows. And that current and that VDS voltage sets the Q point. So that is how the transfer characteristics looks like for a MOSFET. So this is the input voltage and that is the output voltage. When the input voltage or VGS is less than the threshold voltage, there is no ID flowing through the resistor RD. So that means in this equation, this term is equal to 0, or looking at the circuit, the ID is equal to 0. So there is 0 volt dropped across RD. So that means all VDD is available now at the output VDD. So until the voltage VT is reached, that happens. So once the VGS is more than the threshold voltage, the current will go as a square of the applied VGS. So it rapidly decreases, because if the current goes as a square of the input voltage, this minus term reduces VDS as the square law. Right? It goes much further until the condition reaches here as VDS less than VGS minus VT. So beyond this point, or in this section of saturation, the condition is VDS is greater than VGS minus VT. Okay, so once that condition is not satisfied, then it goes into the triode mode. So that's shown here. This is the starting of the triode mode, point B, and at the point B, the condition is VDS is less than VGS minus VT. So that goes into the triode mode. And for amplification, we need the saturation mode, and we set the Q point in the saturation mode. Okay, so you know the significance of the Q point. So you were seen in the lab last week for BJT, what happens when you don't set the Q point at the center, right? What have you noticed? Yeah, so there is in the amplification, some part of the signal, when it goes to one extreme and it gets clipped off. So it's not a pure sine wave anymore. So in the FFT, you will see more frequency components. So in the real world, that will manifest as noise or distortions. Okay, so I believe this audio system is accurately reproducing my voice, but if the Q point was not set properly, then you will hear extra noise, like hissing noise or the higher harmonics that what I'm speaking. So it'll be less quality audio. Okay. Any questions on that? No. All right. Now let's look at. So we saw what happens when we just look at the DC. We saw the voltage transfer characteristics. We set the Q point according to these two equations, one for ID and one for VDS. So that'll give us the current that flows through here. So it'll set the VDS. So consider now we superimpose a AC small signal, okay, on top of the DC signal. So same equations apply, but now VGS is the combination of DC plus AC. And finding ID is same equation, again the new VGS. So VGS is equal to the DC plus AC. Then ID is equal to half Kn VGS plus VGS minus VT the whole square, right? So that is, A plus B the whole square. You apply that here. ID is equal to half Kn VGS minus VT the whole square plus two VGS minus VT times the AC part plus VGS the whole square. So expanding that, you get half Kn VGS minus VT the whole square plus VGS or Kn VGS minus VT times the small VGS plus half Kn VGS square. So you see that when you apply both AC and DC, the ID contains three parts in the equation. Can you tell me which is the DC part from here? The first one. The first one contains just DC because you don't see the small letter VGS there. The second part contains both DC and AC. And the third part contains just AC. So which is the amplified signal here? Is it the A, B, or C? Are you sure? So I am sending a signal like this. What I want is an amplified signal like this, or with a phase shift the other way. Here what it gives me in the C is the square of the sine wave, which will look like this, right? So that's not what we want. We want the accurate reproduction of the input, but in an amplified form. So the B, that is where the amplification happens. Okay? So how we can get rid of this DC part? We can just use a coupling capacitor, right? So that will give us the second plus third term. So the second term is the most useful term. And we need to get rid of this, the third term as well. So third term is so if the condition is Kn VGS minus VT VGS, this should be much greater than half Kn VGS square. That will mean that we can ignore this term, right? So there is VGS in both. So we can take one VGS out. We can bring the 2 there. And Kn is there on both sides. We can get rid of Kn as well. So if the condition VGS is much less than 2 times VOV, if this condition is met, we can actually ignore the third term. Okay? And if it is not met, we will have that high frequency components in the output. So this is the condition to make sure that we are applying only a small signal. So VGS value has to be small, right? So let us look at the useful part there. That is just taking the AC part alone. ID is equal to Kn VGS minus VT times VGS. Have you seen equations like that before? This is like Ohm's law, right? V is equal to, or V by R is equal to I, or V times conductance is equal to I. Or 1 by R is the conductance term. So here I write it like that. I is equal to sigma V. Can you relate these two equations? This is I, and this term is equivalent to the conductance term, and this is the voltage term. So this part, Kn, this is actually the DC part, right? Kn VGS minus VT is called the transconductance, or GM, of the MOSFET. Okay? So why is it called the transconductance, not just conductance? It's because it's relating it's not like this equation where a current flows through the same resistor where a voltage is applied across the resistor. This is about you apply voltage at the input and the current flows at the output. So it's a cross-referencing. So that's why it's called the transconductance of the MOSFET. So we usually denote it as GM. Okay, so when in a problem you're given the parameters for Kn and you know the DC operating point of VGS and the threshold voltage is known, you can find the transconductance. And if the transconductance is given, you can find one of the other parameters as well. So when you apply in this voltage transfer characteristics, you will see when you apply a small VGS at the input, you will see a large oscillation of the output. And you will notice that it is 180-degree phase shifted. So when the voltage is increasing, the output is actually going down. So that's a phase shift of 180 degrees. And we will see that in the small signal model where that 180-degree phase shift comes from. Questions? All right. Okay, so we have discussed this. So everything I write here, I included a slide with a proper, more neat writing. So this is our transconductance, or GM. And this formula we can write as ID is equal to GM VGS, just like we saw before. So that's nothing but Ohm's law, where current or voltage is equal to resistance times current, or current is equal to voltage times conductance. Okay, so this is the transfer characteristics of the MOSFET, where you have VGS, which is the input on one side, and the drain current ID on the other side. So as you see, when you increase VGS from 0 to positive values, there is no drain current flowing because it is less than VT, or less than the threshold voltage. So there is no channel formed, no current flows. So once it crosses the VT, there is a square increase in the ID, because ID is as a square of the VGS. And once you set the Q point, a very tiny region around the Q, you can assume it as linear. If that condition called VGS less than 2 VOV is met, you can consider this as a linear region, and you can find a slope to that. So what is the slope of this curve? So how do you find the slope? Is delta y divided by delta x, right? So delta y is delta ID, and delta x is delta VGS. So it is the conductance, I divided by V. It gives you the conductance. So this is the general formula. So when the delta tends to 0, or when the delta is really, really small, using calculus equation we can write that is the derivative of ID with respect to VGS. Okay, that's just the standard definition of a limiting function. Any questions on that? On that maths? So there are different ways that you can write transconductance. So the first we saw it is GM is equal to Kn VGS minus VT. So that's what we just found, right? Which is Kn times the overdrive voltage. So the same equation we can write in different forms by substituting either for the overdrive voltage or for Kn. The other equation that we use to substitute that is the ID equation. ID is equal to half Kn the overdrive voltage square. So let's substitute for overdrive voltage. What is VOV? This is ID. 2ID divided by Kn root 2, right? From this equation. So if you substitute for that here in the GM, so GM is equal to Kn times root 2ID divided by Kn, which is 2ID divided by Kn root. So that's one way of writing GM. And using the same equation, we can substitute for Kn as well. So what is Kn here? Using this equation, Kn is equal to 2ID divided by VOV square. So we know GM is equal to Kn VOV, and replace Kn with this new value or new expression. That will give you 2ID VOV square times VOV. So one VOV get cancelled. So you have a new equation for GM. So sometimes in the problems you may be given no value for Kn. So that doesn't mean that you cannot find the transconductance. Okay? Don't just rely on that equation. You should be able to transform that equation to either of these equations that you can find the value for GM. Yes?
The first GM we found, why is it root 2ID over Kn still? Root 2ID Kn.
Where is which one?
The rightmost equation.
Here? This one?
Yes. It will be root 2ID Kn.
Oh, right, yeah, sorry. Yeah, you're right. Thank you. Yeah, any other question? All right. Okay, so we use MOSFETs for voltage amplification. So let us see what is the maximum possible voltage gain that we can get from a MOSFET common source amplifier configuration here. So we know the input side, the input is VGS here, and the output we take is across drain and source. So output is VDS. The voltage amplification factor AV is delta VDS divided by delta VGS. In the limiting case, this goes as the derivative of VGS with respect to, derivative of VDS with respect to VGS. So what is VDS? VDS is given here. VDS is VDD minus ID RD. VDS is VDD minus ID RD, which is same as VDD minus half Kn VGS minus VT the whole square times RD. Okay, that is just by using the equation for ID. So in order to find the voltage gain, what do? Need to find the derivative of VDS with respect to VGS. So if you do that to this equation, what do you get? What is the derivative of VDD with respect to VGS? Calculus, anybody? 0 minus about this term. Half Kn 2 VGS minus VT times RD, right? So that's from d by dx of x square is equal to 2x. So that's what we used there. So voltage gain maximum is equal to negative Kn VOV RD. Okay. And we know that Kn is 2ID divided by VOV square from our last slide. So you can replace Kn here. So AV is equal to negative 2ID VOV in the numerator and VOV square in the denominator will give you VOV in the denominator times RD. Okay, so this is the AV max, or the AV max amplitude would be just that without the sign. That is the maximum possible amplification that we can get for this configuration. And what is the real amplification? So that is the maximum amplification that we can get. What would be the real amplification? VDS is VDD minus ID RD. And if you consider both AC and DC, that is VDD minus the DC part plus the AC part times RD, that is VDD minus ID RD minus the AC part. So VDS is also the DC output plus the AC output, which is this equation, VDD minus ID RD minus the small signal part. So we are only interested in the AC, not the DC part. So we can just consider the AC part, which is the small letter VDS, is equal to VDD minus IDRD is the DC part. This gives us the DC part of VDS. So we are not interested in the DC. We can block it out using coupling capacitor. The remaining is just minus IDRD. Which is same as minus GM VGS RD. Okay, because we found that ID is equal to the transconductance times the input. So this is the actual amplification that we get. Or, so this is the output and this is the input. So output divided by input is minus GM RD, which is the voltage amplification factor. So we have a question here. Before that, do you have any question? Okay, so can you try to find the maximum voltage gain possible if a MOSFET has VT is equal to, or threshold voltage 1 volt, and the MOSFET parameter Kn is equal to 1 milliamps per volt square? So you have 4 options here. Do you want me to go to any of the previous slide? Wait. Okay, this is the formula for the maximum voltage gain. Two ID RD divided by VOV is the maximum voltage gain. Now it became very easy, but I want to see how many people make it wrong. What is the maximum value of IDRD that you can have here? So in order for the AV max, you need to maximize this as well, right, on the right side. So what is the maximum value that IDRD can have? The maximum it can have is what? 15. So it cannot be more than 15. So for small values of IDRD will be small. For the maximum value of ID, or the maximum possible ID through this MOSFET, the ID value will be what? IDRD will be, the whole 15 volt will be dropped across here, and there will be 0 voltage across the output, right? So IDRD would be the maximum, and maximum is 15 volts. So that is 2 times 15 volt divided by 201. 2 minus 1. What? I think somebody was playing too much with that. All right, so the answer is 30. Okay, 2 times 15 divided by VGS minus VT. Right? Any questions there? Do you know why you got it wrong? Who got 2? Like, how do you get 2? Do you want me to explain why it is 30?
Yes.
Okay. So we found from the formula that AV max is 2ID RD divided by VOV, right? To maximize the voltage gain on the left side of the equation, you need to maximize the terms on the right side. So the maximum, the VGS is given already 2 volt. You don't know ID, but you know what the maximum value for ID RD can be. If ID is 0, ID RD is 0. ID is maximum, ID RD will be all dropped across RD. So that is the whole 15 volt. So when ID is quite large, the whole 15 volt can be dropped across this resistor, and then 0 volt will be at the output. So ID RD, which is here, can be go up to 15 volt, right? So that is where this 15 comes here as ID RD. So 2 times maximum value of ID RD, which is 15, divided by the overdrive voltage, which is 2 minus 1, will give you 30 as the maximum amplification. So,
wasn't about the maximum voltage gain, supposing a large example.
yeah.
Then we have to solve the ID, isn't it?
You don't have to solve the ID, because even if you solve the ID, you will get probably the same equation, same answer. No, not exact same, but because there is a voltage drop here as well, VDS will still be there. It doesn't go into complete 0 volt. Maximum it goes into is the triode mode, and in triode mode you still see there is a output voltage there. right? Do you know what I'm talking about? This graph here. So it doesn't go to 0. It only goes to 0 at very high voltage. Okay, so there is still a VDS across. But the maximum value of, or the minimum value of VDS can be 0. In that case, the maximum value of ID RD will be the same as VDD, because maximum current or all voltage applied here dropped across RD and nothing was left for the output of the MOSFET. So that is why you don't need to find ID. So it's much easier way is to find what would be the maximum value of ID.
We also know that AB equal to KN VOV RD.
ID is KN VOV RD, yeah.
AB equal KN VOV RD.
Yeah.
Yeah. So if we maximize maximum of AB, it means that on the right side is also have to maximum. But we know the value of KN. We also know the value of VOV.
Yeah.
And RD2.
Yeah, so you can find ID as well there.
In the formula, you gave us the AB on slide 60.
Which one is that?
60.
16 here.
The above formula, AB equal to minus KN VOV RD.
IV is equal to, yeah.
And in this, for the example, we have KN equal to 1.
Yeah.
We have KN, we have VOV, and we have RD. How we can find the maximum value?
So you're saying that we know Kn here,
Yeah.
we know V overdrive here, and how do we find the RD? So it's just 2. Yeah. So that's not the maximum gain. Yeah, so in order to find the maximum gain, so it is derived from the same formula. The 16. The modulus of the maximum gain. So you can get as 2ID divided by VOV times RD. Right?
It's similar to this question. If we substitute the value for ID,
Yeah.
replacing it with half Kn square upon the into overdrive voltage,
Yeah.
the value still doesn't come up to 30.
Really? So this is
This means that if we use that formula, the AB should be a constant, then it cannot reach maximum voltage.
yes, you're right. Kn
That doesn't make any sense here.
Kn VOVRD. Yeah, you're right. I mean, I see that point. So it should be 1 milliamps per volt square times 1 times 2K, right? Two. Let me get back to that on that. I'm a bit confused as well. Yeah. You can't vary it. Yeah, that's true. Yeah, you should be able to use that formula as well to maximize AV. So let me see why it came out like that. I will put it in the more solved examples thing, this one, okay?
Similarly, if you solve with the task vectors formula,
Yeah.
GM something, answer becomes 2. It's not
It's
like for all of the formula, we will take approaches with 2.
I think the problem is that you need the RD because when you maximize it, when you are changing your RD to maximize the voltage, so that RD should not be given.
That's true. So if you maximize ID, the RD will not remain the same. You need to reduce RD. So there is a constant somewhere there. They're right. Okay. Yes.
Another question on the last part we had here. Like you said VT is 1 volt.
Yeah.
And VT is the threshold voltage, right? But we have applied 2 volts in the gate to source. So it's not actually, it's actually the gate switch is on. So but you said the VDS is almost close to 0. Like, and the current is actually flowing, right?
Yes. So
Entirely being consumed by the 2 cable resistor.
true. So you apply a 2 volt here at the gate, and 1 volt is the threshold voltage. So the equivalent voltage that the gate sees is the overdrive voltage, which is 2 minus 1 is 1 volt. Okay, so that's not going to make a difference, but the other point is valid, that if you want to maximize ID, you have to reduce RD. So it won't be 2 kilo ohms. So you may have to use the other formula and get 2 as the answer. Okay, so I will correct this, and thank you for pointing it out. So this is like some last minute examples. Okay, let's see if we get this right, or if I get this right. So what is the small signal voltage gain in the same situation? So the previous was for the maximum voltage gain. Okay, here what is the actual voltage gain of this circuit? What formula will you use that for? Yeah, so AV is equal to negative GM RD. So RD is known, GM is not known. But can you find GM out? How do you find GM? GM is Kn VOV, right? VGS is given, so MVT is given. Correct. So you're absolutely right. It's negative 2 volts. Okay. All right. So any other questions here before we move on to the other topic? Yes. No. I'm not ignoring you, just I'm right-handed, so turn this way. Okay. So we have covered this. Just want to refresh your memories. The IV characteristics. This is the output characteristics, VDS versus ID. So VDS is the output voltage and ID is the output current. So as the VDS increases from a low value to a high value until some point where VDS less than VGS minus VT. It is in the triode mode, and once VDS is greater than VGS minus VT, the ID saturates, so it becomes flat, so no more increase in VDS will increase ID. What can you tell me about the resistance here? R is equal to 0 or infinite? Infinite. You can just think about it. Even if you increase voltage, the current doesn't change. Okay, that means infinite resistance. Or you can find the slope. You can find delta V divided by delta I. So delta V is, let's take this delta VGS divided by delta ID is 0. No change in current, which will give you the resistance as infinite. So this is a particular value for VGS. So if you increase the VGS you apply to the input, your N channel will be thicker, so you will have a family of curves which saturate at higher and higher values of ID. That is shown here. So for a smaller value of VGS, or for 0 value of VGS, you have cutoff here, and once you cross the threshold voltage, then you start to get some ID, and the ID will saturate at different values depending on what kind of, or what is the amount of the gate to source voltage that you apply, which determines the thickness of the N-type channel, which determines the amount of current that flows in saturation. So at the input side, or the input voltage versus the output current, we have seen that until the threshold voltage is applied, the ID is equal to 0, and beyond that it increases as a square of the input voltage. And what is the slope? If you find the slope here, what do you get? So you get delta ID divided by delta VGS, which is the transconductance, right? And you found that the gain is GMRD. So the steeper the slope, the more your amplification will be, right? You can see that also just by drawing here and projecting that same point at the output. If the slope is very shallow, your output will be very similar to the input, and if the slope is very steep, you get high magnification. Okay, so it's halfway through, so we'll take 2 minutes or 1.5 minute break with questions. Do you have any questions? Yes.
Yeah, I asked you this question before, and I forgot the answer you gave me.
Okay, must not be a good answer then.
At pinch off, we have infinite resistance, right? So why is there still a current flowing from the drain to the source to the drain?
Okay, so at pinch off, that's a good question. I remember that's the same question I asked when I learned about MOSFET. So at pinch off, we saw the channel is getting to a point that there is no thickness to that channel, or channel thickness is 0. But still there is a current flowing because you have an applied voltage up to a point that the channel is pinching off. So when you increase the voltage further, the channel recedes backwards, but still the voltage is increasing, so there is still a current flowing through tunneling. Yeah. So we will see that here in the channel length modulation. So this is a slide I made last year because there were a lot of slides or a lot of pictures like this floating around on Facebook, what my parents think I'm doing and what I'm actually doing. But I don't see that anymore, so it's lost its relevance. I need to redo this slide. But this is what it is. So what you think would happen is the drain current saturates. The drain current saturates, and we found that the resistance is infinite. But in reality, it does not saturate to a constant value. So we see that as VDS increases beyond that saturation, the output, the ID also increases. So when the slope is not flat, it now is a finite resistance. It's not an infinite resistance anymore. It is a finite resistance that comes as that appears as the output resistance of the MOSFET. Okay, so we will look at that property now. So that voltage, if we backtrack this this ID curve that increases with VDS, actually it increases linearly. If you trace it back, it will intersect at a point called early voltage. Okay, this was discovered by a scientist called Dr. Early, so that is why it's called the early voltage. So that voltage is denoted by VA, and that happens because of the channel length modulation. So you know that this is the MOSFET equation. ID is equal to half Kn W by L VOV square. But usually write half Kn VOV square. The Kn is equal to Kn dash W divided by L, which we have covered before. So as the length of the channel L decreases, the ID increases, right? So that is the primary reason why we have the increasing ID with the decreasing channel. And that is what gives rise to the early voltage. Imagine if it was flat, what would be the early voltage? 0 or infinite? It should backtrace to negative infinity, right? So early voltage will be infinite, and the output resistance also will be infinite. But because of this channel modulation, we have a finite value of output resistance and a finite value of early voltage. Yes?
Understand how because the distance between two terminal is constant, it cannot change. So when the length of the reduce, then how the current continue to flow when it
Yeah, that is because to reduce that length or reduce the channel length, you need to apply more and more voltage, right? The voltage is increased. That is why the length is reducing. And at some point, it's actually tunneling through that point. even without a channel. It is like it's like dielectric breakdown. So if you have a dielectric which does not conduct current, if you apply a voltage across here, no current flow, and you apply more and more, at some point it just punches through. Okay, so that is the current flows like that. So it tunnels through, and it tunnels from the edge of this channel to the drain really quickly. Any other questions? All right, so I want to derive the equation for the channel length modulation. Okay, so in the next slide, it is given. I don't want to write, maybe I'll write. Do you want me to write down the steps? Okay. But this is important, especially if you are going to design some high frequency MOSFETs in the next few semesters. This becomes quite handy because channel length modulation is something that you have to deal with. So let me go through this quickly then. So you know this formula, you're familiar with that. The drain current is half Kn dash W divided by L VGS minus VT the whole square. So we didn't write Kn, instead we wrote Kn dash W divided by L because we want to take that property. We are looking at that property L. Okay, so we can't write Kn, we just split or expanded it. So we get that term with L in there. So I said when the channel length reduces, the equation gets modified like this. So instead of L, now you have L minus delta L. Delta L being the distance where the channel receded towards the source side. So this was L before, from source to drain, the whole length. And now delta L, it receded delta L towards the source. Okay, so you put L minus delta L as the final length here, and if you take the L term outside, you get 1 divided by 1 minus delta L divided by L. So the equation to remember here, the mathematical equation you need to remember here is 1 divided by x can be expanded as 1 plus x squared plus etc. if x is much less than 1. So that's the condition. X should be much less than 1. In that case, 1 divided by 1 by x can be expanded like this. Okay, that's a mathematical formula that people use. Or in number theory, it's there. Just like we have e power x is equal to 1 plus x squared by 2 factorial plus etc. So it's an expansion like that, 1 divided by 1 minus x. So we made use of that. So you can see this is like 1 divided by 1 minus x, x being delta L by L, and we know that delta L is quite small compared to the total length of the channel. So that x is less than 1 or much less than 1. So we can write it as 1 plus x, which is 1 plus delta L by L. So that is the final equation. So you see that that equation has two terms. One is half Kn VGS minus VT whole square, and then a sum term, half Kn WL divided by L with delta L divided by L there. So that equation has two terms, and the first term, if we write it, is ID is equal to half Kn dash W divided by L VGS minus VT the whole square plus half Kn dash W divided by L VGS minus VT the whole square times delta L VDS divided by L. Okay. So delta L is proportional to VDS. Delta L is proportional to VDS, or we can write delta L is equal to a lambda dash times VDS. Okay, because of the properties of proportionality, you can multiply with a constant and equate it. And delta L divided by L is lambda dash divided by L VDS. We call that lambda dash divided by L as lambda. So this is the lambda that you saw here as the inverse of early voltage. Okay, that is by definition by the discoverer. So that equation is finally rewritten as this one. So here you can see the same two terms are there. So first term is this one, this factor here times 1, and the second term is this factor here times lambda VDS. Yes.
Lambda VDS over L.
Lambda,
The last thing.
this one.
In the formula, you write 1 over 2 Kn W over L. And yeah,
This one.
should be lambda VDS over L.
Lambda VDS over L. Oh yeah, yeah. Yes, sorry. Right. Thanks. So there are two parts of this equation. The first part is the ID, which if you had no early voltage. And the second part is the lambda VDS times the ID. So you know where the increase in current coming from.
Isn't it just lambda VDX? In the formula, ID. I think you just need
Oh, L is right there, right? Yeah. This one, right? You're talking about this? Yeah? Yeah, so L is taken outside here, right? So yeah, so here is the second term that makes the ID increase further, because that depends on VDS. While the first term, there is no VDS term. So no matter how much you increase VDS, the ID would not have changed. But because of the second term, lambda VDS, as you increase VDS, the ID also will increase. Okay? So in the problems, how it is going to be asked is you are given the early voltage, like early voltage is say 200 volts. You need to find the output resistance. Okay, how do you find? If you know early voltage, how do you find the output resistance? R0 is VA divided by ID. Okay, so it's a linear relationship, so the Ohm's law applies here. So you can find R0 is the early voltage divided by the drain current through that. Okay. Now we have seen this before. we can replace the MOSFET with its small signal model when we are doing a small signal analysis. So this is on the left side here is the small signal model without the output resistance, or without considering the early voltage. So once you consider early voltage, you have an extra resistance at the output R0, which is equal to VA divided by ID. Okay, any question on that? Okay, how do you draw the equivalent circuit for this configuration? So what do you do first? Draw the equivalent circuit for the MOSFET, which is at the input. So you draw the gate, drain, and source. Between the gate and source, there is no resistance or infinite resistance, but there is a voltage VGS. From drain to source, there is a current that depends on the voltage VGS. So the current is GM VGS. And if the early voltage is considered, you will have R0 at the output. And where does RD come in the picture? Where do you connect RD? Between drain and the VDD. VDD is grounded in the small signal analysis, right? Okay, where do you connect RG here? It goes from gate to drain here. So what can you say about input resistance? So if there was no RG, your input resistance is infinite because there is no current flowing into that MOSFET. So IG was 0. But because this RG that connects from gate to drain, now you have an input resistance which is not infinite. How do you find it? Who thinks it is RG plus R0 parallel RD? Who thinks it is RG plus R0 parallel RD? Is it true? No. So what is it? So you're looking into here to find the input resistance. How do you find out? You find out by finding the voltage and the current, right? The current is flowing in I in. So what is the V in? VGS. And we need to find I in. It's more complicated than finding the VGS. So I in, one part of I in. Okay, so what is going through here? I in minus GM VGS. Okay, so I in comes in, GM VGS goes this way, and I in VGS goes in this way. So let's write V in is equal to I in times RG plus I in minus VGS times R0 parallel RD, right? And V in is equal to VGS. Now, taking our VGS to one side, is 1 plus R naught parallel RD is equal to I in times RG plus R naught parallel RD. Is it correct? GM So what is VGS divided by I in? It's equal to RG plus R naught parallel RD divided by 1 plus GM times R naught parallel RD. Okay. So will you be able to derive this and put values to find the input resistance if you asked in a problem? So if you're given a circuit like this and asked to find the input resistance, all the values are given, RD, GM, all values are given. First you need to draw the equivalent circuit. Then you need to find V in divided by I in, put the values in, and then find the input resistance for the exam. Okay? So, yes. Someone? Any questions on that? So I've put around 15 problems, solved problems in the more examples section. So don't look at the answers. So try to do the question. Try to complete the answer yourself first. So only when you get stuck, look at the answers. Okay. Now going to the high frequency behavior, you saw that we had internal parasitic capacitors for BJTs. In the MOSFETs also we have internal parasitic capacitors. But do you expect the capacitance to be more or less compared to BJT? More? People who did lab yesterday knows about it more. We have, why is it more in a MOSFET? Why do you think the internal capacitance are more or more of a problem for MOSFET?
Because the depletion region is thicker than in BJT. In this case, we have the P channel, so the atom will feel much more than the BJT.
Yeah, right. So in BJT, there are many reasons. First, in BJT, the area of the capacitors are less. In a MOSFET, it is spread over a wider area. And second, we have a accumulation of N channel or P channel, depending on the MOSFET, right below a gate. So this is like a really flat metal plate, and underneath you have a lot of charge. So that is charge is separated by a short distance. So you have a lot of capacitance there. You have a depletion capacitance throughout this area. So the total capacitance in a MOSFET is quite high. So how does it impact its frequency performance? Yeah, the gain goes down much earlier in frequency. So if the BJT can operate up to 200 megahertz, the MOSFETs can operate only much below that. It will not go up to 200 megahertz. So generally we can divide these distributed entire capacitances as just like what we did for BJT, at the input and also bridging the input and the output. So without any capacitors, this was our small signal equivalent model. So with capacitor, we will add a capacitor VGS and another capacitor VGD. just like this. So this is similar to what we have done for BJT, and so the analysis also will be very similar. So here is maybe you have seen this exact plot in your first lab in the simulation for a BJT in the second lab. Yeah, for BJT you saw it in the first lab, right? So this is applicable to every devices or every systems that we have. So every electronic system is frequency dependent. So when you have coupling capacitors at low frequency, the coupling capacitors offer a high impedance, so signal cannot come into this amplifier, and also the output cannot go to the output of the amplifier. So that is why your gain is much lower at a lower frequency. As the frequency goes higher, the coupling capacitors become invisible to the signal. Now they act like a short circuit, so you get a high frequency or high gain, which it maintains for a bandwidth of frequency. Then, because of parasitic capacitors, it comes down again. So the one side, this is due to the coupling capacitors, and this is due to parasitic capacitors on the high frequency side. So the flat region is the highest magnitude of the voltage gain, and we call that the midband. Okay, so we talked about 3 dB frequencies. So the frequency at which the power becomes half, or the voltage become 1/√2, are these 2 points, and the frequency corresponding to that is the high frequency FH and FL. The difference between FH and FL is the bandwidth of that particular device. In MOSFETs, usually people refer to unity gain bandwidth. So unity gain is when the input is equal to output, or the amplification is equal to 1. Okay, usually it is much higher, 5 or 10 or 30, but because the amplification goes down, at some point the input to output ratio will be just 1. And what would be the dB value of that? 0, which is log 1. 20 times log 1 is 0. So that is the 0 dB frequency, and if you take this bandwidth, that is called unity gain bandwidth. Okay, or we call it WT or omega T, or sometimes it's FT, or unity gain bandwidth, for T for transition. So just like in BJTs, we can try to find the short circuit gain or short circuit current gain of this MOSFET. So to find the short circuit current gain, what do? We short circuit the output and give a current at the input and see how much is the current output modified. So here I0 is equal to GM VGS minus this current, right? GM VGS minus SC gate to drain VGS is equal to VGS times GM minus SCGT. What is VGS? VGS is the input current times all these resistances, all these impedances here, right? So R naught doesn't come in this picture here because there is a short circuit across R naught. So no current want to go through R naught. Everything will go through this resistor. So VGS is the input current times the impedance of CGS plus CGD, because they are now in parallel, because there is the short circuit here. So they are like two parallel capacitors. So that is I times 1 by S CGD plus CGS. So we can find I naught divided by II, which is the short circuit current gain, as VGS times GM S CGD divided by VGS times S CGD plus CGS. So that is from these two equations. So VGS is common, and this term compared to GM is quite small. So you can write it as GM divided by S CGD plus CGS. So this is your short circuit current gain, and you can see that this is different from BJT. So BJT was in the form A naught divided by J omega divided by omega naught, right? And this is not in that form. There is no 1 plus term in the denominator. That is why using unity gain bandwidth is more appropriate for MOSFET than a BJT. Because this, if the equation was this, there would be a definite breakpoint like that. So it's more appropriate to talk about 3 dB breakpoint. Here, it is always decreasing like that. So there is no definite breakpoint per se. So we will talk about unity gain bandwidth and unity gain frequency. Okay, so that is mostly what I wanted to cover in this lecture. Before going to the summary, I want to get a feedback from you on this. This is not going to affect the questions you're going to get for the assessment. If you say very confident, I'm not going to give you tough questions, it's already set. So if you are struggling, I don't know who it is, but if you are struggling, please make use of the help that you're going to get from me and David. So you are always welcome to come for any personal session. You have questions, bring your questions. If you don't understand any part, just tell me that I don't understand this part at all. Can you explain it again? And I can try to explain it in a different way that you are happy. And here, if you have any specific feedback, now the whole class can see your feedback. This is the time, this is your moment. Class party, no. Unless it's a political party that everybody want to vote. Yes, please vote. Yes, it will have it. It will have sound this time. So there are too many buttons here in this panel. The last time there was video was muted. That's it. Eid Mubarak to you too. It's on Friday. So I'm going to lock this now. Okay, not very useful for me. Okay, so what we have learned in the last 3 weeks in the lab and also in the classroom is mostly it was a review of what you have learned before. So you learned about diodes, MOSFETs, and BJTs, the structure of this device, what makes them work, what are the internal structure. There is quite a lot into the device, solid-state device physics, which is way beyond the scope of this unit. So we couldn't go to that much detail, but I tried to show you some band diagrams, but that is nowhere even scratching the surface. But it's a whole unit by itself, just to learn what is a diode. So, but we don't want to go in that much depth. So we learned the structure of these devices, how they operate, how do you bias them, how do you give them, set the Q point, what current, what voltage will you give, how to see the IV characteristics. You know what IV characteristics would look like. You can find out what voltage would be at what current and stuff like that. And we did some small signal analysis, tried to find internal capacitances, and from that do the high frequency analysis just by using the same techniques but adding the two capacitors in there. And in the lab we learned simulating and implementing this. Implementing part hasn't come yet, but you will soon implement the circuits in the next week. So 2 more things. I have added a 15 solved or semi-solved practice questions on these 3 weeks topics. So that covers quite a lot of range of questions. And the answers are also there, but in a mirror imaged way. So don't look at the answers, try to do it yourself. So next week I won't be coming to the lecture. David Payne will be talking to you about differential amplifiers. Okay, and I will be back with mixers and nonlinearity after week 6. Yeah, thank you everyone. You've been wonderful. I'll see you soon. So yeah, if you are struggling, if you really think you are struggling, please come to see me. You will not be punished for that. On the other hand, you will be helped. Okay? Thank you.
So I have a question.
Yes.
For the N channel MOSFET.
Yeah.
With